So welcome back. You've been dying to know how to do these proof problems and some of these examples in section 7.3, so I'm going to show you how to do it. Now we have this problem, example 3, where we're given that FG is congruent to GH. Okay, so let's go ahead. I'm going to color coordinate this. So we have this, and so GF, GH, those two are congruent. We're also told that these sides, JK and KL, are congruent. And then our last piece of given information is angle F is congruent to angle J. And that's the only thing that these two triangles share in common so far. And we're asked, our task is to prove that these two triangles are similar. That's what this little symbol here means. Let me go ahead and highlight that for you just in case you didn't remember. This means similar. So how do we prove these triangles are similar? Well, let's get some clues from above first, just to have an awareness of where we're headed. So we can either prove them that they have all sides proportionate, that they're similar, or we have two sides with an angle between, makes them similar, or that we have two angles that are similar, or all three angles. So let's go ahead and see how we can go about this. The first step we always do is we're going to start with our givens. The givens must lead us somewhere, so let's go ahead and start with that. So we have this, and that is given. Okay. I kind of like proofs if I were a student, from a student perspective, because if you're listing the givens, look, those are easy points. You just start with the givens, and you got some points right there. Then we have angle F congruent to angle J, and of course that's given. All right, now this is where probably a lot of people get stuck. Where do we go from here? Well, the reason why this particular triangle gave us that two sides are congruent. It didn't say that FG was proportionate to JK or anything like that. It just said that these two sides are congruent. So what does that mean? How would that potentially help us find more pieces of information about these two triangles? Because remember, we need either all the sides proportionate, but we only have two sides. And we can't find the third side because it's not a right triangle. We don't know it. Now we can't do a side angle side because it's not a side right here. The sandwich, remember these two sides have to be sandwiched between that angle. There's the angle. We don't have enough information there. Okay, and the other piece of information was we don't have two angles. But maybe we can find an additional angle. How would we go about that? Well, if we know that these two sides are congruent, what else do we know? Well, we know that they're isosceles triangles. Isosceles triangles. So let's think for a second. We can say, all right, we can say triangle FGH and triangle JKL are isosceles. Okay, and then the reason why is because both triangles with two congruent sides are isosceles. That's a reason. Or you could put like definition of isosceles triangle, okay? Because we already told that we have a side and a side congruent there, okay? So they're isosceles. Now, what does that mean? How does that help us find more information? Can't help us find a side, but it can help us find an angle. Okay, we know this angle. Let me make it red, actually. No, it's like gold. Okay, we know that this angle is also congruent to the other side. Why is that? Well, that's the definition. I can't remember the exact theorem for it, but we can say, hold on. Let's get this out. Let's do this right. We're going to say angle H is congruent to angle F. Angle H is congruent to angle F. And angle J is congruent to angle angle L. Why is that? Well, that's because we can say, what's a good way to say this? We can say definition of isosceles triangles, definition of isosceles triangles, or probably better yet, you could say something like the isosceles triangle congruent base angles theorem. And I'm not sure if that's the actual name, but at least to me, this tells this tells me that you understand that base angles of an isosceles triangles or of isosceles triangle is congruent, or they are congruent. Okay, so that's why sometimes just writing it out helps a little bit. Okay, now we have two angles in both. What does that mean? Well, we could say that these two triangles, well, first, let's rewind. We know these two angles are congruent, but now we know that these two angles are congruent also, okay? There's a couple different ways we could go here. We could also say now that angle H is congruent to angle L. That's probably the next step we need to say. Okay, so we're going to say, and I'm going to use purple just because it's a different color. Angle H is congruent to angle L. A couple of different ways to do this. We can say probably the law of syllogism here, because if angle H is congruent to angle F and angle J is congruent to angle L, and we already knew this, angle F is congruent to angle J, then it's the law of syllogism, okay? So it's just connecting one idea to another. So law of syllogism. I think it's one L. Syllogism. Maybe it's two L's. Something doesn't look right. I'm going to do a quick spell check real quick. So I think it's, yep, it's two L's. I knew it. Should have gone with my gut. Syllogism. Okay. So law of syllogism. We can say law of syllogism there. Now we can say what? We can end with the final line. FGH is similar, H is similar to triangle JKL. And why is that? Well, we were told that we have this angle similar and this angle similar. So that is a similarity. And that would be our final answer, okay? Kind of a, I don't know, it's a tough proof for sure. But it walks you through some of the components that we need from the whole year. So that's what's kind of cool about this particular proof, is it walks us through all the theorems and types of things that we've used in previous chapters all in one problem. So that's why I like that one. Okay, now we have more of like a real world relevant problem, because I know tons of us are trying to figure out how tall a mast is when we're standing on a pier. Okay, very common problem for most people. But let's go ahead and figure this out. So let's say this person's 6 feet, and they put a mirror on the ground that's 8 feet away. And they already know that the boat is 40 feet away, and they want to be able to measure the mass. And there's actually reasons that this problem could have been relevant back in times where, you know, we don't have as much sophisticated instruments. But how do we set up this problem? What do we do to solve it? Well, the first thing we got to recognize is we got to recognize that we have two triangles being formed here. We got this triangle, okay, this green one, and I like to redraw it below also. And then we also have, I'm going to go blue. I like blue. It's a great color, my favorite color. So there we go, we got blue. We have two triangles here. All right, now what do we know about these triangles? Well, we know that if there's a mirror, that these two angles are congruent. Okay, that's one of the first things we need to know. This mirror makes those two angles congruent right here because it bounces off at exactly the same angle. The other thing we got to assume here is that this person's standing straight up, perpendicular from the ground, and this boat's mast is perpendicular from the ground. Otherwise, it's not a very good boat, okay? So we got to assume this. Based on this information, what can we say about this green and blue triangle? Hopefully you guys recognize it. We know it's a similarity. Now, just as a recap, we've been saying a similarity a couple times already. How do we know that? Well, if these two angles and these two angles are congruent, that means the third angle has to be congruent based on the third angle's theorem. And if the third angle is congruent, all three angles are congruent, then that's the definition of similarity. All the angles congruent, okay? So that's the reason why a similarity exists. Okay, now let's get back to the problem. So we have this is 6, this is 8. This is 40, and this is unknown, so we're going to call it, we're not going to use X, we're going to use Z. How about that? So we're going to use Z. Or, I got a better one. M. Sorry to make you erase, but M for mast. Now, a couple different ways we can set this up. I've been talking about this in some of my other videos, but all we need to do is set up a true proportion. So we can do two things. We can compare the small triangle to the big triangle. okay? We can compare the small one to the big one. And as we do that, again, we need a proportion. So we need something on the left and something on the right. Well, on the left, we can compare the short sides, and on the right, we can compare the long sides. That's one way to do this. Another way to do this problem is to compare the short side of one triangle versus the long side of that same triangle. Then what do we do on the left and right? Okay, because remember, we have to have something on the left and right. We could compare the dimensions of the small triangle versus the dimensions of the big triangle. You're probably like, whoa, too much information, okay? If that's too much information, let's just go into this first example where we compare the small triangle to the big triangle for each measurement. So we have, for the small triangle, the short side is 6, okay? Now the big triangle, its short side is M, okay? It's the shorter side, M, and we get that visually, okay? This is the short side, so this vertical component also has to be the short side because they're similar. Okay, now let's go to the long side. For the small triangle, the long side is 8. And for the big triangle, the long side is 40. Okay, so there's our proportion. Let's go ahead and solve before I show you the next one. So we're going to cross multiply. We get 8m equals... Now, actually, one thing you can do is you can simplify this first if you want. So we know 8 divided by 40 is 1 over 5. You can do that. Sometimes that makes more sense to do. So I'm going to go ahead and actually show that. I'm going to rewrite the proportion. Okay, so I'm going to reduce first. This is helpful when you want to save yourself from big multiplication. So 1 over 8. 8 goes into 45 times. Divide both the top and bottom by, not 5, 8. Okay, so we get 1 over 5, and then we cross multiply, much easier. We get 1m equals 30. Okay, so we know the mass is 30. What is the measurements? 30 feet. 30 feet tall. Okay, pretty tall mass. Okay, now let's show how we get the same thing by comparing the short and long side of both the small triangle and the big triangle, keeping the dimensions of the small triangle on the left and the big triangle on the right. So this time we're going to go, okay, the short side of the small triangle is 6, and the long side is 8. So here we're just comparing this to this, okay? And if we compare short to long of the small on the left, we got to compare short to long of the big triangle on the right. So we go, m is the short, 40 is the long. Okay, you're not thinking, oh man, this isn't the same. What are you talking about? We have different fractions, but we can reduce still. We can divide the top and bottom by 2, and we get 3 over 4 equals m over 40. So now we cross multiply. We get 4m equals 120. We divide by 4, we get m equals 30 feet. See how we got the same thing? I think that's pretty cool. Now, the reason why it works is because we're making two comparisons that are true. We're keeping everything the same. Here we had all the small dimensions on the top, all the big triangle dimensions on the bottom. Here we had all the short sides on the top, all the long sides on the bottom. Here we had all the short sides on the left, all the long sides on the right, all the small sides on the left, all the small triangle components on the left, all the big triangle dimensions on the right. As long as you stay organized like that, you're fine, okay? The one thing you can't do is switch these around. You can't put all of a sudden the 40 on the top, and then, what was the other one? And then the 8 on the bottom, because the 8 doesn't belong to the big triangle and the 40 doesn't belong to the small triangle, okay? So you can't do that. You just have to make sure everything stays organized based on your initial proportion setup. So understanding this, let me highlight it. Understanding this, how you have top and bottom, left and right, top and bottom. If you can understand this component of proportions, everything else falls into place. Please check out some of my other videos where we practice this same concept. I hope you enjoyed this one, and I look forward to seeing you next time on West Explains Best.